Why is the sky blue? A question so simple, a child could ask it, and often does. Yet buried inside it is a far more unsettling truth. The sky isn't blue. Not really. And whatever you think you're seeing when you glance upward on a sunny afternoon, well, it's not what's actually happening. Not even close. Tonight, we're going to take that apart, gently. The color of the sky is a lie told by scattered light, bent molecules, and our slightly gullible eyes. What we'll explore is not just why the sky appears blue, but what that illusion tells us about the nature of light, the limits of perception, and how the universe operates regardless of our opinions on the matter. You'll soon realize the sky doesn't care how you feel about it. Which, to be honest, is quite freeing. Everything you see when you look up is the result of invisible processes playing out between sunlight and air molecules. And those molecules don't know they're creating a visual spectacle. They're just doing what physics tells them to do, like badly paid extras in a drama they don't understand. There's no intention, no goal, just cause and effect, from the sun to your retina. Along the way, we'll examine the physics of scattering, the evolution of our eyes, and what early humans made of the blue above them long before anyone invented a telescope. We'll look at the atmosphere as a filter, light as both wave and particle, and reality as something that doesn't necessarily need your permission to be complicated. But don't worry, this won't be fast, and it won't be flashy. This is the kind of quiet, patient exploration that doesn't try to impress you. It just points at the sky and calmly says, "You've been wrong about that for years." And not in a rude way, just in a sort of matter of fact, here's what actually happens kind of way. What you'll come to see is that the universe has rules. It follows them perfectly, with no concern for beauty or meaning. Sometimes, by accident, those rules produce something stunning. A blue sky, for example. But they do it the same way they produce storms, black holes, or tax audits, entirely without malice or favor. By the time we're done, you'll understand why the sky looks the way it does, why that's not the same as what's actually happening, and what that difference tells us about how little of reality we're built to see. And if that sounds a bit existential, well, it is. That's part of the charm. This leads us to consider the question itself, and why something so ordinary has such strange, far-reaching answers. The question is simple: why is the sky blue? It's one of those things we all accept without much thought, like why bananas curve, or why socks vanish in the wash. But unlike socks, the sky doesn't hide the answer out of spite. It hides it in physics, light, and human biology, and that makes it a surprisingly tricky thing to pin down. When we ask why the sky is blue, we're not really asking about color. We're asking about how light travels, how matter behaves, and how our brains process the result. It's a question that sounds local, but opens the door to a much larger view of the universe. Because to truly answer it, we have to admit that what we see isn't always what's there. Human curiosity works like that. We see a thing, assume we understand it, and move on. But sometimes we stop and ask the oddly specific question and end up discovering an entire system of natural law. The sky's color is one of those gateways. What starts with sunlight ends with quantum particles, planetary atmospheres, and evolutionary biology. It turns out there's no blue pigment in the sky, no surface or layer reflecting that color back at us. In fact, the sky isn't really a thing at all, just the result of photons from the sun interacting with the gases that make up Earth's atmosphere. And how those photons scatter is a matter of probability, not preference. The sky is blue for reasons it didn't choose. there's also a twist. The sky isn't just blue. It changes constantly, from deep azure to gray to orange to black. And yet we call it the blue sky, as if that's its true nature. But what we see depends on where we stand, what time it is, what's in the air, and how our eyes work. Reality hasn't changed, just our relationship to it. That's what makes this question interesting. Not because it reveals a hidden secret, but because it shows how often we mistake appearances for truth, how often we let our senses tell the whole story, when really they're only narrating the surface. The deeper truths sit underneath, quiet and uninterested in whether or not we notice them. So, tonight, we'll look at what light is, how it behaves, and why our atmosphere interacts with it in just the right way to create the illusion of a blue sky. Along the way, we'll take in some quantum mechanics, a bit of history, and the occasional sarcastic comment about human eyesight. Because if nothing else, we've earned it. This leads us to consider how our own experiences shape what we believe, and why our personal perception of the sky might be the least reliable thing about it. You've seen the sky. You've probably pointed at it, taken photos of it, or muttered something about the weather because no one knew what else to say. The sky is one of the most constant things in your life, always there, quietly looming overhead. And yet, odds are, you've never really thought about what it is you're looking at. When the sky is a clear blue, it feels familiar, safe even, as if it's always been that way. But what you're seeing isn't a solid surface or even a fixed color. It's light, scattered by particles, filtered through atmosphere, interpreted by your brain, and labeled blue out of habit. Which is fine. Except it isn't really blue, not in any absolute sense. Here's the odd part. If you stand somewhere else, say, on Mars, the sky isn't blue at all. It's more of a dusty butterscotch. Same sun, different atmosphere, different result. On Titan, Saturn's moon, you wouldn't see blue either. More of a murky orange. So it turns out the universal color of the sky is not universal. It's just what Earth happens to offer. And it gets worse. That familiar blue isn't even consistent on Earth. It shifts depending on where you are, the time of day, what particles are floating about, and even how much water vapor is in the air. But your brain doesn't care. It smooths all that variation into a single, stable impression. Sky equal blue, case closed, nothing to see here. But of course, there is something to see. The very fact that we all accept this color without question makes it more interesting, not less. Because the more automatic a belief is, the more likely it is to be wrong in some important way. And in this case, the thing we all see is the result of a complex, invisible process that none of us are actually perceiving. You probably trust your eyes. They're quite good, to be fair, but they're tuned for survival, not for accuracy. What they show you is a version of reality that's useful, not necessarily true. The sky looks blue to you because of how your brain interprets the available light. It's not a direct download of truth, it's more of a compressed file with bits missing. This is why the blue sky matters, not because it's particularly rare or special, but because it feels obvious, and anything that feels obvious is worth questioning. The fact that you're convinced of the sky's color says more about how your brain works than how the universe does, which, depending on your mood, is either fascinating or mildly insulting. This leads us to consider what we're actually looking at when we see the sky, and how those impressions are shaped by forces far beyond our senses. Look up on a clear day, and what do you see? A wide, uninterrupted dome of soft blue stretching from horizon to horizon. It seems calm, permanent, and strangely flat. The kind of thing you'd struggle to explain to someone who's never seen one, like trying to describe the color warm or what a headache feels like. You know it when you see it, or do you? The sky appears to us as a solid canopy painted with gradients of blue and white. It doesn't look like air, it doesn't look like a gas, and it certainly doesn't look like something you're sitting inside. But that's exactly what it is. You're not under the sky, you're in it. You're breathing part of it. You are, to be precise, inside a thin layer of atmosphere clinging to a spinning rock. But your brain doesn't process any of that. It simplifies. It presents you with a color, blue. A single quiet answer to the chaotic mess of photons, molecules, angles, and timing that's actually taking place. It's an impression, not a direct observation. The sky looks like a smooth sheet, because your mind prefers easy explanations over true ones. Honestly, who doesn't? This appearance also shifts with time. In the morning, it's pale and cool. By midday, brighter and harsher. In the evening, it deepens or turns orange. Clouds drift by, light changes direction, and pollutants scatter new wavelengths. Yet through all of this, you still call it the blue sky. It's the scientific equivalent of calling every cereal cornflakes and hoping for the best. There's something called perceptual constancy, a feature of your brain that helps keep things looking the same, even when they're not. It's useful for not walking into walls every time the light changes. But it also means you overlook detail. When it comes to the sky, your brain quietly edits out the complexity and replaces it with "sky is blue, move on." This mental shortcut is practical, but it's also misleading, because the sky's color isn't fixed. It's the result of a constant interaction between sunlight and atmosphere, observed from a particular location through a particular set of eyes. What you see depends entirely on when and where you are, and what your biology allows you to register. If you had different eyes, one's more sensitive to ultraviolet or infrared, you'd see a very different sky. Not better, not worse. Just different. There's no correct version. Only the version your species evolved to notice. Which is a slightly humbling thought. The most reliable feature of our world isn't even the same for all creatures on it. This leads us to consider the scales we're dealing with, the sizes, distances, and energies at play when sunlight hits our atmosphere and starts to do strange things. To understand why the sky appears blue, we need to step back quite a long way. Because what looks like a simple splash of color is actually the result of interactions happening at vastly different scales. From the size of atoms to the distance between Earth and the Sun, each part plays a role in the illusion. It's a quiet tug-of-war between the very small and the very large. Start with the Sun. It's about 150 million kilometers away and emits a range of electromagnetic radiation, including what we call visible light. This light travels through space, mostly uninterrupted, until it reaches Earth's atmosphere. There, it meets particles much smaller than the width of a human hair, nitrogen, oxygen, and the occasional bit of dust or water. Now, the light itself isn't just white. It's made up of many wavelengths, different sizes of electromagnetic waves, all traveling together. The blue part of that spectrum has a shorter wavelength, roughly 450 nanometers. That's less than 1,000th the width of a grain of sand. If that sounds small, it's because it is. Physicists got very excited about it. Everyone else moved on. When this light enters Earth's atmosphere, something curious happens. The shorter wavelengths, the blues and violets, get scattered in all directions by those tiny gas molecules. The longer wavelengths, like red and orange, pass through more directly. So, the sky becomes filled with this scattered blue light coming from every direction, even though the sun is in just one spot. It's like watching a single bulb light up an entire room by bouncing off every surface. But in this case, the bulb is a star, the room is the atmosphere, and the walls are mostly invisible. And your eyes? They're just trying to make sense of the chaos. Not always successfully. The human scale, the few feet around your body, is comfortable and familiar. But the processes that shape sky color play out on completely different levels. Photons, molecules, planetary atmospheres, solar output, all operating on scales you can't see, but depend on every time you look up, whether you know it or not. From this perspective, the idea of a blue sky becomes something much stranger. It's not a surface, not a substance, not even a fixed effect. It's an emergent phenomenon, a product of interactions between waves and matter, played out on a stage many times larger and smaller than ourselves. As ever, nature doesn't explain itself. It just carries on. This leads us to consider how this scattering actually works. The physical process that takes a beam of sunlight and turns it into a sky full of color. Light behaves in odd ways. It's a wave and a particle. It travels in straight lines, except when it doesn't. It can be invisible or blinding. But tonight, we only need to focus on one particular behavior: scattering. Specifically, why certain wavelengths of light get deflected by the air, and why that deflection turns our entire sky into a soft blue backdrop. Sunlight might look white, but it's actually made up of many different wavelengths, each one corresponding to a different color. When that light reaches Earth's atmosphere, it runs into molecules of nitrogen and oxygen. These molecules are small, really small, and they don't just absorb the light or let it pass through. They scatter it, bouncing it off in different directions. This process is called Rayleigh scattering, named after Lord Rayleigh, who, in a very calm and thoroughly British way, figured it out in the 19th century. The key idea is this: shorter wavelengths scatter more than longer ones. Blue and violet light are short, red and orange are longer. So, as sunlight hits the atmosphere, the shorter waves get knocked about far more easily. It's not that the blue light is removed from the beam entirely, it's just that it gets flung sideways, upwards, backwards, everywhere. And when you look up, what you're seeing is all that scattered blue light bouncing around the sky. The red and yellow wavelengths travel straighter, heading off toward sunsets, distant hills, and presumably people with better weather. This scattering happens constantly. Billions of photons hitting billions of particles at all angles. It's not organized. There's no coordination. Just countless little deflections happening all at once, governed by probability and wave behavior. In the end, it creates something that feels smooth and natural, but is anything but simple. If you're wondering why this doesn't result in a violet sky, since violet scatters even more than blue, hold that thought. We'll get there. For now, just know that what you're seeing is the result of light being redirected by the tiniest things in the atmosphere, with the shorter wavelengths getting flung around like toddlers on too much sugar. And this isn't some rare, delicate event. It's happening every second, across the entire sky, all around the world. The moment there's light and atmosphere, Rayleigh scattering starts. It doesn't wait for your permission. And it certainly doesn't care if you've brought sunglasses. This leads us to consider the next layer of detail, how our eyes and brains turn that chaotic scattering into a single, stable impression of color. So, we've established that Rayleigh scattering takes the sunlight and flings the shorter wavelengths, especially blue and violet, across the sky. But if violet scatters even more effectively than blue, then logically, shouldn't the sky be purple? And yet it's not. This is where biology steps in and quietly ruins the physics party. Human eyes aren't neutral observers. They've evolved to be just good enough to keep us from walking into trees and possibly spotting a tiger in the bushes. We have 3 types of cone cells. Sensors in the retina that respond to different wavelengths of light. One type is most sensitive to red, one to green, and one to blue. You'll notice there's no violet cone. We can detect a bit of violet, but not much. The blue cones do some of the work, and the rest is interpreted. Basically, our brains make educated guesses about what we're seeing, and they often round everything in that short wave range to blue. Violet is there, technically, but we're not wired to see it properly. Evolution had priorities, and nuance wasn't one of them. To make things even more skewed, the sun emits less violet light than blue to begin with. The solar spectrum is strongest in the green-blue region. So between lower violet input, our eyes' weak sensitivity to it, and the brain's love of simplifying things, the sky comes out looking blue. Not purple, not lavender. Just plain, sensible, widely accepted blue. Then there's a second factor. When all this scattered light reaches our eyes, it's not pure blue. It's a mix of scattered wavelengths, with blue dominating. Our brains process that blend and assign it a label. That label is sky blue, a color category created by perception, not physics. If another species with different eyes looked at our sky, they might describe it very differently. This interaction between physical light and biological perception is what makes color so slippery. Color isn't an inherent property of things. It's a result of how light interacts with matter and how our visual system interprets the outcome. In a way, the sky isn't blue, it just looks blue. Which, to be fair, is also how a lot of people handle their taxes. And yet, this imperfect filtered view gives us a consistent experience. Even if it's technically an illusion, it's a reliable one. Our brains process the scattered light, compare it against memory and expectation, and present us with a stable world, one that includes a friendly blue sky, even if we're only getting part of the truth. This leads us to consider how this same scattering process plays out beyond Earth. Across the cosmos, under different skies, guided by the same natural laws, we now understand that the sky appears blue because of how sunlight interacts with Earth's atmosphere and how our eyes interpret that scattered light. But Earth isn't special in having an atmosphere. Other planets, moons, and even comets have atmospheres too, of varying thicknesses and compositions. And wherever there's light meeting gas, scattering happens. Take Mars, for example. Its atmosphere is thin and mostly carbon dioxide. Because it's far less dense than Earth's and contains different particles, Rayleigh scattering doesn't work in quite the same way. The result? A sky that appears more yellowish-brown in daylight and curiously blue at sunset. The opposite of what we see on Earth. Same laws, different outcome. Titan, one of Saturn's moons, has an atmosphere thicker than Earth's, made mostly of nitrogen and methane. Here, sunlight is scattered and absorbed in such a way that the sky looks a murky orange. Not quite the kind of place you'd go to top up your holiday snaps. Still, the underlying physics remains unchanged. Photons meeting molecules and getting redirected. And it doesn't stop with planets. Even in the vastness of interstellar space, light from distant stars is scattered by dust and gas. This can cause stars to appear redder than they are, a process known as interstellar reddening. It's Rayleigh scattering's more distant cousin, operating on a much larger scale. Again, the same principle, just stretched across light years. This consistency is worth pausing over. The same physical laws that shape the sky above your house also determine what the sky looks like on a planet halfway across the galaxy. These are not local quirks. They're universal properties of light and matter. Unaffected by your location, your mood, or whether you remembered to bring a jacket. It's easy to think of sky color as something aesthetic, like choosing paint for a ceiling, but what you're actually seeing is a visual consequence of unchanging laws, applied to whatever happens to be in the way. The composition, thickness, and behavior of the atmosphere simply determine which wavelengths scatter and how we perceive them. That's what makes Rayleigh scattering so powerful. It's a basic, predictable interaction, yet it plays out in endless variations. From Earth to Mars, from Titan to nebulae, light continues to scatter in familiar ways. It reminds us that even across the chaotic diversity of the universe, some processes remain stubbornly reliable. This leads us to consider how time fits into the picture. Not just space, but deep time. How has the sky's color changed over the lifespan of Earth? And how might it change again? It's tempting to think the sky has always looked the way it does now, but like everything else on Earth, it's changed, and it will continue to change. The blue sky we see today is just one version. A snapshot in a long, unsettled timeline shaped by atmospheric chemistry, solar evolution, and an unfortunate habit of the planet occasionally trying to reset itself. Early Earth, over 4 billion years ago, had no oxygen in its atmosphere. It was filled with gases like methane, ammonia, and carbon dioxide. Not exactly the ingredients for a bright blue sky. If you'd looked up back then, assuming you weren't immediately suffocated, you might have seen a hazy orange-brown dome, like standing inside a rusted saucepan. Not particularly inviting. It wasn't until photosynthesizing microbes evolved, around 2.4 billion years ago, that oxygen started accumulating. This kicked off the Great Oxygenation Event. Over time, as oxygen levels rose and nitrogen stabilized, Rayleigh scattering became more dominant. That's when the sky began shifting towards the familiar blue we now associate with daylight. It wasn't instant, but nothing geological ever is. The sun hasn't stayed the same either. It's gradually become brighter over billions of years, changing the intensity and quality of the light it sends our way. Combine that with evolving atmospheric conditions, volcanic eruptions, asteroid impacts, biological changes, and you've got a sky that's been in constant flux. The idea that it's ever been stable is, quite literally, a fair weather illusion. Even in the last few centuries, human activity has altered the way the sky looks. Pollution can scatter light differently, creating hazy skies or exaggerated sunsets. Tiny particles, like soot or sulfates, affect how light is absorbed and redirected. In extreme cases, volcanic eruptions have made the sky appear red or grey for months on end. So if the sky's blue feels permanent, it really isn't. Looking ahead, as Earth continues to warm and ecosystems shift, atmospheric composition may change again. Add in long-term trends like solar evolution and possible mass extinctions, and it becomes clear that the blue sky is a temporary phase. Beautiful, yes. Familiar, certainly. But fixed? Not remotely. From a cosmic perspective, even 1 billion years is short-lived. Eventually, the sun will expand, Earth's atmosphere will boil away, and the sky, whatever color it is by then, will vanish altogether. Which might sound grim, but the truth is, the sky doesn't owe us consistency. It just reflects the current state of things, no more, no less. This leads us to consider the deeper reality behind all of this, that the sky's color, like much of nature, is the product of systems that work without intention or concern. Systems beautifully indifferent to whether we happen to be watching. If the sky feels like it was designed for us, it's only because we're here to notice it. The blue above isn't there for our comfort or our photos. It's the accidental result of light and molecules following physical laws, with absolutely no concern for human satisfaction. The universe didn't pick blue for aesthetic reasons. It didn't pick anything at all. Rayleigh scattering isn't trying to make things lovely. It's just what happens when electromagnetic waves hit particles smaller than their wavelength. There's no intention, no design brief. It works the same on Earth, on Mars, in a lab, or in a cloud of interstellar gas. The fact that it sometimes creates something we call beautiful is entirely incidental, like a sandwich looking a bit like Elvis. Nature functions on rules, not wishes. The sky is blue because that's what those rules currently produce under the conditions we live in. If the air were thicker, or made of different gases, or if our eyes had evolved differently, we'd be having a very different conversation. Possibly about how calming the lime green sky looks on a Tuesday morning. This is the quiet brilliance of science. It reveals that beauty doesn't need purpose. The universe isn't performing. It's not trying to impress us. The fact that it often does, despite having no motivation to do so, is perhaps the most grounding truth we can hold. What we see is the side effect of forces that are, frankly, indifferent to whether we're here or not. And, in a way, that's comforting. There's something oddly peaceful about knowing the universe just works. With no bias, no exception, no special case carved out for humans. The same scattering that makes the sky blue also explains why sunsets go red, why smoke looks gray, and why distant mountains fade into the horizon. It doesn't play favorites. This indifference isn't cold. It's consistent. That consistency is what makes it possible to understand the world at all. If light scattered differently on Tuesdays or decided to take weekends off, science would be impossible, but it doesn't. It just continues, reliably, impersonally, beautifully, with or without our appreciation. So the blue sky isn't a message, it isn't a gift, it's just a coincidence of laws and light, of air and vision. And yet, we still find meaning in it, we attach feelings to it, we write poems about it. But the sky? It doesn't care. And honestly, that might be the most generous thing about it. This understanding prepares us to consider how humans first started noticing the sky, and what we did with that curiosity once we stopped assuming it was just painted on. Long before anyone knew what molecules or photons were, people still looked up and wondered. The sky, with its shifting colors and changing moods, became a source of myth, explanation, and the occasional bit of panic. Without science, early humans did what humans do best. They made up stories. Some of them were creative. A few were surprisingly close. Most were wildly off. To ancient civilizations, the sky wasn't a product of physics, it was structure. In many cultures, it was imagined as a solid dome, often held up by mountains, gods, or animals. The ancient Egyptians thought it was the body of a goddess arched over the earth. The Norse imagined a sky made from the skull of a giant. You can't say they weren't trying. The Greeks had a go as well. Aristotle believed the heavens were made of a perfect fifth element, ether, separate from earthly matter. To be fair, he was doing his best with no telescope and a philosophy degree. The idea of the sky being part of a fixed, unchanging realm persisted for centuries. Elegant, neat, and wrong in just about every measurable way. Still, they weren't totally clueless. Many early cultures noticed that the sky changed. It darkened at night, it went red in the evening, it clouded over and cleared again. These were people who relied on the sky for survival, for navigation, for planting, for reading the weather. They paid close attention. They just lacked the tools to explain what they saw. Color, in particular, was treated as symbolic rather than scientific. Blue skies often meant good weather, clear vision, and the favor of the gods. Red skies brought warnings, omens, or change. And in the absence of spectrometers or atmospheric models, that interpretation made perfect sense. They weren't wrong to ask the questions. They just didn't yet have the maths. What's remarkable is how consistently people across different parts of the world tried to understand the same thing: why the sky behaves the way it does. Whether in China, Mesoamerica, India, or the Mediterranean, people asked the same questions. They just came to very different conclusions depending on what tools and beliefs they had available. And they did all of this without written science, without controlled experiments, and often without the luxury of being wrong twice. Yet they observed patiently, recorded what they could, and passed it down. That willingness to notice patterns, even when the explanations were off, laid the groundwork for what would come much later. This leads us to consider how some of those early ideas gave way to clearer understanding, and how a few curious individuals started to push past myth into method. Gradually, the shift from mythology to method began. People started not just to describe the sky, but to question it. Instead of assuming the heavens were fixed or divine, they wondered if the light itself had properties, something measurable, not mystical. It was a small shift in thinking, but one that opened the door to everything that followed. One of the earliest known figures to seriously study light was Ibn al-Haytham, working in the Islamic Golden Age over 1,000 years ago. He didn't have modern tools, but he asked the right kinds of questions. He explored how light traveled, how it bounced off surfaces, and how it entered the eye. He also understood that observation needed structure. Basically, he brought logic to the light show. Centuries later, Isaac Newton took things even further. Using a prism and a dark room, and a lot of stubborn curiosity, he showed that white light wasn't pure. It was made up of many colors, which could be separated and recombined. This was a major turning point. The colors of the sky weren't added to light. They were already inside it, just waiting to be split. It's easy to forget how strange that idea must have seemed. The default assumption had been that color was a property of objects, or a feature added by the eye. Newton's work helped reveal that light carries all the color, and matter just filters it. A rather rude awakening for anyone who thought blue was a special heavenly shade instead of a scattered wavelength. But Newton didn't figure it all out. He focused mostly on what light did, not what it was, and he wasn't terribly fussed about the sky's color specifically. That would come later, with scientists like John Tyndall and Lord Rayleigh, who dug into the mechanics of scattering and wave behavior. Still, Newton cracked open the door. The rest just walked in after. What matters here is how these early insights were gained. Not through grand revelations, but through small, patient steps, careful observation, simple tools, and a refusal to stop asking what if. Long before light could be broken down mathematically, it was split by hand, by lens, by thought. Science at this point wasn't about specialization. It was general curiosity applied methodically. These thinkers didn't know where their ideas would lead. They weren't solving the mystery of the blue sky. They were just poking around at how light behaved when no one was telling it what to do. And that was enough to change everything. This leads us to consider the role of tools, how instruments began to expand our senses, and how technology helped us see what was always there, just out of reach. Human senses are useful, but they've got limitations. Our eyes can't see ultraviolet. Our fingers can't feel individual atoms. Our ears, thankfully, can't hear molecules colliding in the atmosphere. To get beyond the limits of our biology, we needed help. That help came in the form of tools, instruments designed to make the invisible visible, or at least measurable. The prism was one of the earliest and simplest of these tools. By splitting white light into its component colors, it showed that light wasn't uniform. With just a bit of glass and a beam of sunlight, people began to realize that what looked like simplicity was hiding complexity. That was the beginning. Then the devices got fancier, and the questions got harder. The spectrometer came next. This tool allowed scientists to measure light in precise wavelengths. Now, they could record exactly how much blue, red, violet, or green was being emitted, absorbed, or scattered. Suddenly, sky color wasn't just an observation, it was data. You could graph it, quantify it, argue about it in slightly passive-aggressive academic journals. With better lenses and precise filters, experiments moved indoors. Artificial light could be shone through various gases to observe how they scattered. By isolating variables, changing the gas, altering the pressure, shifting the angle, scientists could replicate aspects of the sky in a lab setting. Essentially, they were bottling the sky without needing a weather forecast. Atmospheric studies also improved with height. Weather balloons and, later, satellites gave researchers a view of the atmosphere from above. Instruments on board could detect how sunlight changed as it moved through different layers of air. Measurements of albedo, how much light the Earth reflects, added even more precision to our understanding of light behavior on a planetary scale. Different types of scattering were identified and classified. Rayleigh scattering small particles, short wavelengths, explained the blue sky. Me scattering larger particles, like dust and water droplets, helped clarify why clouds are white, and why haze makes things look pale and washed out. It turned out the sky had quite a few tricks, and we'd barely scratched the surface. The tools didn't just confirm what we saw, they often contradicted it. Light that appeared white to our eyes showed strong blue or violet signatures in measurement. Conditions that looked identical to us produced very different spectral data. The instruments weren't correcting our vision, they were showing us just how bad we were at trusting it. This leads us to consider how, despite these advancements, many early explanations were still wrong, and how scientific progress often includes the awkward process of admitting that you've misunderstood something for decades. Even with better tools and more data, the road to understanding the sky's color wasn't exactly smooth. Science, for all its progress, still relies on human interpretation, and humans are famously not great at getting things right the first time, or the second. In fact, much of scientific advancement is just a polite way of saying, "We used to think this, but we don't anymore." One common early misconception was that the sky's blue color came from reflections of the oceans. It seemed logical enough. Both are blue, both are large, both are above or below us, depending on where you're standing. But it turns out that air doesn't reflect color in the same way water does. And anyway, even if it did, inland skies would look quite different. Which they don't. Others believed that air simply had a blue tint, as if the atmosphere were lightly dyed, like a poorly rinsed pair of jeans. But gases are colorless. What we perceive as color is a result of light scattering, not pigment. Once again, it was easy to assume the sky looked blue because it somehow was blue, a kind of visual shortcut that ignored how light behaves. There were also plenty of attempts to explain the sky's color using vague concepts like vapors or mists, without defining what those were. It was a time when anything that couldn't be directly observed got labeled as some sort of mysterious atmospheric thing, which is fine, unless you actually want to understand anything beyond. Something's probably up there. As experiments became more refined, these old models began to fall apart. The data just didn't support them. Spectral measurements didn't match the ocean reflection idea. Artificial atmospheres didn't show any blue pigment. And mathematical models of scattering started to reveal patterns that previous theories couldn't explain. Slowly but steadily, the fog lifted. This wasn't failure. It was part of the process. Science doesn't promise perfection, it promises self-correction. Every flawed idea, tested and abandoned, brought researchers closer to a working explanation. Being wrong, repeatedly and thoroughly, was not just acceptable, it was necessary. A bit like cooking, except with fewer edible results and more air molecules. What's also worth noting is how often these corrections were met with resistance. People don't enjoy letting go of ideas that feel obvious, especially ones they've believed since childhood. But scientific knowledge doesn't care how satisfying a theory feels. It only cares whether it matches reality. And that's why, eventually, the better explanation wins. This leads us to consider how scientists began using experiments, not just instruments, to test and isolate the mechanisms of scattering, building a more complete picture through direct investigation. Understanding why the sky is blue didn't come from staring at it and guessing. It came from experiments, carefully designed, often tedious, occasionally frustrating tests meant to isolate the processes involved. No dramatic light bulb moments, just methodical work, lots of patience, and the odd moment of, "Wait, is that it?" followed by another round of checking. One of the earliest experimental approaches to sky color was carried out by John Tyndall in the 1860s. In a darkened lab, he passed light through clear containers filled with fine particles suspended in gas. What he noticed was that shorter wavelengths, the blue ones, were scattered more than the longer, redder ones. The effect mimicked the way the sky behaves. Finally, something visible and repeatable. Tyndall's work wasn't just observation. It was controlled demonstration. He changed particle types, varied concentrations, and compared the results. This allowed scientists to see the effect of scattering in real time, and to confirm that it wasn't just the gas doing the work, but the size and nature of the particles suspended in it. The term Tyndall effect is still used today to describe scattering in colloids. Later experiments went further. They isolated individual gases to confirm that even molecules as simple as nitrogen and oxygen, when small enough, could scatter light on their own. Using pressurized chambers and filtered light sources, researchers tested the way light behaved under different conditions. Blue scattering was strongest when the particles were much smaller than the wavelength of light, a key feature of Rayleigh scattering. More complex setups introduced polarized light, light where the waves are aligned in one direction, to examine how different alignments affected scattering. By rotating filters and measuring angles, scientists could map how scattered light changed depending on where it was observed from. This helped explain why the sky can look paler at the horizon and deeper overhead. Importantly, experiments didn't just confirm theories, they corrected them. Some early models assumed the atmosphere was full of floating dust or vapor droplets. But experiments showed that even pure gas, free of impurities, could scatter light in the way the sky does. That was a turning point. The blue didn't need particles floating about. The gas molecules themselves were enough. Even today, experimental methods continue to improve. Laser-based scattering tests, atmospheric modeling in wind tunnels, and high-altitude balloon studies allow for ever more precise measurements. But the principle remains the same. Test a specific idea, isolate a variable, and check whether the data match the theory. If they don't, adjust and repeat, possibly with more coffee. This leads us to consider how these individual discoveries came together across time, language, and geography to form a shared, global understanding of something as quietly universal as the color of the sky. Science rarely moves forward because of one person having a single clever thought. It's more like a long queue of people nudging each other forward, occasionally getting distracted, and occasionally stepping on someone's foot. The explanation for why the sky is blue didn't arrive in a single leap. It was built slowly, across cultures, generations, and continents, by many minds asking similar questions in different ways. While names like Newton, Rayleigh, and Tyndall often get most of the credit, they weren't working in isolation. Each of their discoveries was shaped by earlier thinkers, rival researchers, lab assistants, and colleagues they may or may not have remembered to thank. And in the background, universities, institutions, and, eventually, global scientific networks quietly carried the work forward. By the 19th century, the study of atmospheric optics had become a truly international effort. Scientists in France, Germany, Britain, India, Russia, and beyond were all making contributions, sometimes unknowingly overlapping, sometimes arguing, occasionally agreeing. As with most collaborations, progress was rarely smooth, but the shared goal of understanding light kept the momentum going. It helped that light scattering wasn't politically controversial. No one was storming out of Parliament over whether the sky was blue due to Rayleigh scattering or a divine mood swing. So researchers could share results across borders, via letters, conferences, and eventually published journals, without worrying too much about starting a war over diffraction patterns. This collaborative nature also meant theories were tested and challenged more rigorously. When one team suggested a new model, another might replicate it, revise it, or politely dismantle it with better data. Slowly, a consensus formed. Not because anyone said this is the final answer, but because, over time, the answers that worked were the ones left standing. It also wasn't just physicists. Chemists helped describe the gases involved. Mathematicians worked out the equations. Engineers developed the instruments that made new measurements possible. Artists and photographers recorded visual evidence of light and atmosphere long before color photography was reliable. Everyone played a part, even if some didn't realize they were contributing to the puzzle. And this continues today. Satellite data from one country is analyzed by scientists in another. Open access journals make scattering data available worldwide. Multinational teams collaborate on atmospheric models that explain not only Earth's sky, but also those of Mars, Venus, and exoplanets we haven't even seen yet. The understanding of blue skies is now a global human project. This leads us to consider how far that collaboration has taken us into the realm of precision, into measurements and models that go beyond general explanation, and into detail so fine it can predict the color of an alien sunset. Today, we don't just know why the sky is blue. We can measure it with remarkable accuracy. We can calculate the intensity of scattered light at different altitudes. We can model atmospheric effects to predict what the sky will look like under specific conditions. And we can simulate skies on planets we've never visited, based entirely on numbers. It's all got rather precise. Satellite instruments like MODIS on NASA's Terra and Aqua satellites constantly scan the atmosphere, collecting data on light scattering, aerosol content, and cloud formation. These readings help us build detailed models of atmospheric optics. And unlike your eyes, these machines don't get tired, don't squint, and don't confuse bluish with close enough. Spectrophotometers, devices that measure the intensity of light at specific wavelengths, now operate both in orbit and on the ground. They can detect subtle shifts in color caused by pollution, volcanic ash, or seasonal changes in air quality. If you're imagining someone in a lab holding a prism and squinting at a rainbow, it's a bit more advanced than that now. This level of detail lets researchers model sky color under different hypothetical scenarios. For example, what if Earth's atmosphere had 10% more nitrogen? What if the sun was slightly cooler? What would the sky look like on a planet with a methane-rich atmosphere and a weaker gravity well? These aren't questions we're asking just for fun. Well, mostly not. And it's not just about Earth. These same techniques are being applied to exoplanets, planets orbiting stars far beyond our solar system. By analyzing how starlight filters through their atmospheres during transits, scientists can estimate what those alien skies might look like. Some may be pale green, some may be thick with haze. A few might be bluer than ours, but again, none of it is personal. Modern models of atmospheric scattering also take into account things like refractive index, humidity variation, and even the shape of light paths through turbulent air. It's science at its nerdiest and at its most exact. You can now produce a mathematical curve showing exactly how much blue you should expect in the sky over Norwich at 3 p.m. on a clear spring day. But this precision comes with a small caveat. The more we measure, the more we realize how many tiny variables are at play. The system may follow clear laws, but it's influenced by chaos, ever-changing inputs, layered effects, and occasional unpredictability. Like British weather, really, only governed by physics rather than vague optimism. This leads us to consider the edge of that precision, the places where uncertainty remains, where answers still shift, and where our best models still leave us with honest, unanswered questions. Even with all our data, instruments, and simulations, there are still places where our understanding of the sky remains, politely, a bit fuzzy. These aren't failures of science, but signs that nature is just slightly more complex than we've managed to model so far. And, annoyingly, the sky isn't always in the mood to behave exactly the same way twice. Take twilight, for example. As the sun drops below the horizon, the sky goes through a series of subtle color shifts. We understand the basics: scattering, absorption, and atmospheric layering. But the exact details of why the twilight sky can sometimes turn deep violet or greenish gray are still open to interpretation. It's not chaos, it's just complicated. Then there's the question of aerosols. These are tiny particles suspended in the atmosphere, like dust, soot, or sea salt, and they have an outsized impact on sky color. But their behavior is hard to pin down. They come in irregular shapes, they clump, they reflect and absorb in different ways depending on what they're made of. In short, they don't make things easy. Clouds also present a bit of a nuisance. Not in the obvious ruining your picnic sense, but because their interactions with light are maddeningly varied. The same cloud type can look bluish from one angle and orange from another. Scientists have equations for these effects, but they involve so many variables that even supercomputers sometimes sigh and ask for a simpler task, like modeling the economy. Uncertainty also creeps in at the microscopic level. Molecules don't all scatter light in perfectly ideal ways. Their exact orientation, vibrational states, and surrounding environment can introduce tiny deviations. Normally, these effects average out, but when you're chasing precision, tiny starts to matter. Add to that atmospheric turbulence, which bends light rays in unpredictable ways. It's why stars twinkle, and on rare occasions, it's why the setting sun can briefly appear green, a phenomenon charmingly called the green flash. There are entire papers devoted to figuring out when it happens, why it's so fleeting, and why it always seems to elude you when you try to show someone. And sometimes, the unknowns come not from nature, but from our limits. We can't place sensors in every square meter of atmosphere. We can't sample the air on Mars every morning. So we rely on models, which are very good, but not perfect. Like weather forecasts, they're right more often than not, but don't bet your picnic on it. This leads us to consider the big picture. What does this mixture of understanding and uncertainty reveal about science itself and our place in the cosmos we're so busy trying to see clearly? All this effort to explain a bit of color in the sky might seem excessive. But really, the story of the blue sky is the story of how science works. You start with something simple. Why is it blue? And quickly discover you're knee-deep in fluid dynamics, quantum scattering, planetary chemistry, and statistical modeling. So much for a quick answer. Science doesn't deal in final truths. It works in layers, models, and probabilities. Each explanation adds something, but rarely tells the whole story. The Rayleigh scattering model was a breakthrough, but it didn't explain sunsets. Mie theory handled clouds, but not violet absorption. Every aha moment is followed, sooner or later, by a yes, but. The blue sky also reminds us that everyday things often have deep causes. It's easy to overlook something we see all the time. The color of the sky, the way shadows soften, the slight haze at the horizon. But those things are shaped by vast systems. Air molecules, solar radiation, planetary geometry. Mundane at ground level, cosmic just a few layers up. It also shows us that science doesn't always begin in a lab. Some of the best questions come from simply looking up and wondering. No fancy equipment. just human curiosity and the willingness to admit you don't know, followed by a strong desire to find out, sometimes followed by several decades of math. And the more we know, the more we realize how much we don't. That's not a failure. It's a feature. It means the world hasn't run out of questions. And despite centuries of progress, the sky above us still holds mysteries. There's a kind of comfort in that. Predictable skies might be nice for pilots, but they'd make dull work for scientists. Then there's humility. The sky doesn't change color for us. It doesn't care if we understand it or not. But we care, because we want to make sense of the world, to grasp what lies behind the surface of things. Science is our way of asking politely and occasionally getting an answer back. And it's not just about the sky. The same principles apply elsewhere, from the colors of distant planets to the way we study climate on Earth. Once you learn how to think scientifically, you start seeing patterns and questions everywhere. Some you can answer, some not yet, but you keep looking anyway. This leads us to consider our final question. What happens if the sky isn't blue at all? What do other worlds look like, and how strange can their skies become? So far, we've focused on Earth, a planet with a nitrogen-rich atmosphere, moderate pressure, and just the right scattering conditions for a blue sky. But if you take those ingredients and start changing them, even slightly, the sky's color can shift dramatically. Across the solar system and beyond, some very strange skies are on offer. Though, to be fair, most of them aren't exactly inviting. Take Mars. Its sky is famously tinted reddish-brown, thanks to the fine dust particles suspended in its thin atmosphere. But here's the twist. The sunsets are bluish. That's because Martian dust scatters red light away during the day, but forward scatters blue light during sunrise and sunset. It's like nature decided to flip the script for no reason other than to confuse visiting robots. Venus, on the other hand, has an atmosphere so thick and acidic that no one's ever seen its sky from the surface, at least not directly. Models suggest it would appear a murky yellowish white, dimmed by thick clouds of sulfuric acid. It's like standing inside a very slow-moving fog machine, except the fog is trying to melt your face. So again, not exactly scenic. Titan, Saturn's largest moon, has an atmosphere rich in nitrogen and methane. Sunlight filtering through produces a deep orange haze. During the day, the sky would likely look peach-colored, warm, but in an unsettling sort of way. Think of it as a permanent golden hour, but without the Instagram appeal, and temperatures hovering around 180 C. On gas giants like Jupiter or Saturn, there's no solid ground to stand on, and the sky is just more atmosphere as far as you can fall. Their upper layers are made of hydrogen, helium, ammonia, and water vapor. Colors swirl in stripes and storms, but there's no clear sky in the way we're used to. It's all weather, all the time. Further out, on distant exoplanets, the possibilities get even weirder. Some planets may have skies tinged green or violet, depending on their star's spectrum and atmospheric chemistry. One planet, HD 189733b, likely has deep blue skies due to silicate particles that scatter blue light. Of course, it also rains molten glass sideways at thousands of kilometers per hour, which rather spoils the mood. Even Earth wasn't always blue. When the atmosphere had less oxygen and more methane, the sky may have appeared more orange. And in billions of years, as the sun swells and scorches the atmosphere away, our sky might fade to black once more. cheerful thought, isn't it? So when we say the sky is blue, we're really saying that our sky is blue, for now. But across time and space, sky color is more of a suggestion than a rule. This leads us, finally, to look down at the humans staring up and ask, why does this matter to us? After all the scattering, wavelengths, and planetary comparisons, we arrive at a deceptively simple question. Why do we care what color the sky is? It's not essential for survival. It doesn't feed us, shelter us, or charge our phones. And yet, across time and culture, humans have kept looking up and wondering. Part of it, of course, is basic curiosity. The sky is ever present, yet always just out of reach. It changes constantly, not wildly, but subtly. And that makes it oddly compelling. Much like a neighbor who always seems busy but never leaves the house. You can't help trying to figure out what's going on. The sky has also been a canvas for meaning. Cultures have looked to it for omens, calendars, deities, and direction. Its colors signaled weather, time of day, and sometimes even moral messages. A red sky at night might mean shepherds are delighted, though you'd have to ask an actual shepherd to confirm that. Good luck finding one with signal. Then there's the emotional side. The color of the sky influences how we feel. A bright blue sky can lift our mood. Gray skies are linked with lower energy. These aren't just poetic associations. There's evidence that light levels affect our biology, from hormone cycles to sleep. We're not just observers of the sky, we're participants. And at a deeper level, the sky reminds us that we're part of something vast. That patch of blue overhead isn't a ceiling. It's the thinnest layer of air separating us from space. The sun, the moon, the stars, all visible through that same window. Looking up has always been a way to look out. The study of the sky also pulls together multiple fields of science. Physics, chemistry, astronomy, biology, psychology, all converge when you ask, why is the sky blue? It's a rare question that starts with light scattering and ends with mental health. And somehow, it all still makes sense. Finally, it's a way to remember our place. We live on a planet with just the right ingredients for a blue sky, breathable air, and visible sunsets. It's not too hot, not too cold, and just transparent enough to let starlight in. That's not something to take for granted. It's a fortunate coincidence, or, if you prefer, an outcome of billions of years of chaotic planetary evolution. This leads us to one final reflection. The sky may not belong to us, but how we respond to it does. To look up and wonder, that's very much a human thing. We began with a familiar sight, the blue sky. A feature so ordinary that it's easy to forget it's not a given. Tonight, we followed the journey of sunlight through air, bounced through molecules, sifted by wavelength, refracted by humidity, and colored by chemistry, all to explain something we see every day and mostly ignore, unless it starts raining during a picnic. We've seen how the color of the sky isn't fixed. It changes with the time of day, the angle of the sun, the weather, and the composition of the atmosphere. A blue midday becomes a golden evening. A smoky sky turns brownish gray. And with just a bit more methane or less oxygen, Earth's sky might have looked entirely different. Possibly more Instagrammable, though that's hard to quantify. Our eyes, it turns out, are part of the story too. Human vision is tuned to daylight, not too bright, not too dim, with peak sensitivity in the green-blue range. So what we perceive as sky blue isn't a universal truth. It's a collaboration between physics, biology, and psychology. The atmosphere scatters light, and our brains finish the job. Zooming out, we discovered skies elsewhere, on Mars, Venus, Titan, Jupiter, and learned how color reveals composition. Methane gives one shade, sulfuric acid another. But even on Earth, the sky tells us what's in the air. Pollution, particles, and seasonal changes all leave a visual fingerprint. If you want to know what's floating above you, just look up. Then maybe get a mask. There's also the scale of it. The sky feels close, yet it's just the start of space. The sun's light that fills it is 8 minutes old. The stars visible at night are light years away. Even a simple sunrise links us, indirectly but unmistakably, to the fusion processes inside a G-type main sequence star. Quite the commute. More than that, the sky reflects our place in time. Earth didn't always have blue skies, and it won't always keep them. Climate, atmosphere, and sunlight are all temporary features. The sky we know is just one frame in a long planetary film, and not even the most dramatic one. Still, there's something grounding in that familiarity. The blue above reminds us of home. It connects generations. From ancient skywatchers to today's meteorologists and moody teenagers staring at clouds instead of homework. It's universal, but also deeply personal. So next time you glance up and wonder why the sky is blue, remember, it's not just scattered light, it's everything we've covered tonight. Physics, planets, perception, and a bit of luck. A daily reminder that even the simplest questions can lead to the biggest answers. In the end, why is the sky blue? Might not seem like the most pressing of questions. It's not going to solve climate change or tell us how to cook rice properly. But it does something else. It invites us to look more closely at the world around us, and not just accept it as background noise. Because it turns out the sky being blue isn't just about color. It's about light, atoms, pressure, scattering, chemistry, biology, and perception. It's a question that gently unpacks the entire toolkit of science. The fact that we can trace something so familiar back to quantum mechanics and planetary evolution is quietly impressive, like discovering your gran used to be an aerospace engineer. More importantly, this kind of question shows us how science really works. Not through grand declarations, but by following curiosity. Ask something small, pull at the thread, and before long, you're knee-deep in atmospheric physics, wondering where the last 2 hours went. Not unlike trying to fix a leaky tap and ending up watching a 12-part documentary on plumbing history. It also shows us the limits of knowledge. There are still parts of the sky's behavior we don't fully understand. The detailed interactions between particles and light in polluted air, for example, remain tricky to model, and new observations from Mars, Titan, or exoplanets often challenge our assumptions. So even a settled question keeps evolving. There's also value in how it connects things. The blue sky touches everything from astronomy to psychology. It links distant stars with the cells in your eye. That's a pretty wide reach for a daily backdrop. And, unlike some school lessons, you might actually remember it next time you're stuck on a bench watching clouds roll in. And perhaps that's the point. Questions like this remind us that science doesn't just live in labs or textbooks. It's embedded in the ordinary, in the color of the sky, the warmth of sunlight, the way shadows move through a day, asking why, even when the answer seems trivial, keeps us engaged with reality. So, is Why is the sky blue? A big question. Not in scale, maybe, but in attitude, it's enormous. It's about being awake to wonder without needing to be dramatic about it. Quiet curiosity, steady attention, and a willingness to keep asking. If that's not science at its best, I don't know what is. And so, from scattered photons to thoughtful questions, we reach the end of our night beneath the sky. As twilight deepens, the blue fades slowly to black. The scattered daylight that once dominated the sky retreats, and the stars, always present but hidden, begin to emerge. It's a quiet reminder that the sky isn't an object, it's the name we give to what's above us, a shifting interface between ground and space. By now we've unpacked this familiar blue in full. We've followed photons from the sun, seen how they scatter through air, pass through pollution, and even pick up the faint fingerprints of chemistry and biology along the way. A sky's color is a story of its planet, told through light and filtered through whatever's floating around. On Earth, it happens to be nitrogen and oxygen doing most of the scattering. On Titan, it's haze. On Venus, acid. Mars is more subtle, dust doing the work in a thinner soup. Different skies, different stories. Yet the same laws of physics apply. Photons don't discriminate, they just bounce off whatever's in their way. And when there's nothing to scatter them, then space looks black. Not because it's empty, but because there's nothing there to redirect the sun's light into our eyes. If you ever wanted a stark visual metaphor for isolation, the vacuum of space is quite obliging. So the blue of our sky is a kind of middle ground. It's not sunlight directly, and it's not darkness either. It's light that's been knocked sideways, diluted, and softened by air. That gentle tone we find so calming is in fact the result of constant tiny collisions, rather like family holidays. It's also fragile. Change the thickness of the atmosphere, the contents of the air, or the type of star, and the sky changes color. The blue we see is only possible because all these things happen to line up. Not quite a miracle, but not guaranteed either. It's not clear whether this should make us feel grateful or vaguely anxious. Still, this color, scattered, filtered, and refracted, connects us to something bigger. Every time we look up and see the blue, we're catching the sun's light mid-journey, redirected by our atmosphere, shaped by our planet's physics. A daily connection to the cosmos, without having to leave the ground or pay for space tourism. And then, gradually, it darkens. The stars return. The days scatter, gives way to the night's silence. Tomorrow, the blue will come again. Not because the sky needs to be blue, but because, for now, this is what our air and our sun make together. A fleeting shade of light, scattered into being. The sky, it turns out, is more than just a pretty ceiling. It's also one of the largest and oldest scientific laboratories on the planet. Every day, light pours in from the sun, interacts with gases, dust, water vapor and pollution, and tells us something in return. All we have to do is look up and know what to look for. Historically, the color and clarity of the sky have served as indicators for weather, seasons, and even natural disasters. Long before satellite forecasts, people noticed that a reddish sunset often meant dry weather ahead, while a pale yellow haze could warn of dust or illness in the air. The sky has always been speaking. We've just got better at translating. Today, we do that with tools rather more precise than squinting at the horizon. Spectrometers analyze the light scattered through the atmosphere, teasing out the presence of ozone, carbon dioxide, and even methane leaks. Satellite imaging can track aerosols across continents. LiDAR can build 3D models of air structure above a city. It's basically spy gear for clouds. And yes, the blue of the sky itself is still part of that dataset. Changes in the shade or sharpness can indicate shifts in particle density. For example, during the global lockdowns in 2020, many people commented that the sky seemed bluer. It wasn't just their imagination. Lower pollution meant fewer particles scattering extra light. A slightly purer blue was the result. Scientists also study the way skies look on other planets to learn about their atmospheres. On Mars, a bluish tinge appears at sunset, caused by dust scattering sunlight in the opposite direction compared to Earth. It's like the universe copied the homework, but changed a few answers to make it less obvious. This kind of observation isn't just for fun, though. Changes in atmospheric clarity can signal broader environmental shifts. Warming trends, droughts, forest fires. If the sky starts looking noticeably different over time, something significant is usually happening. Like when your neighbor suddenly installs blackout curtains, you start to ask questions. Beyond Earth, the search for life often begins with skies. When telescopes catch light from exoplanets, they break it apart into spectra. The tiniest hints, say, of oxygen or water vapor, can suggest something interesting is going on. It's detective work on a planetary scale, and our sky has been the training ground. So next time you see a blue sky, remember it's not just scenic, it's data. It's a continuous experiment in physics, chemistry, and environmental change, all conducted above your head. The world's biggest science lesson, conducted daily, free of charge. If you were to stand under a different star, on a different planet, the sky above you would almost certainly look strange. Not just a different kind of strange, but a physics-approved strange. The color, the brightness, even whether you'd see a sky at all, it all depends on a mix of factors you don't get to vote on. Start with the atmosphere. Earth's blue sky comes from having just the right amount of gas molecules to scatter sunlight. But go to a planet with a thinner atmosphere, like Mars, and the effect is reversed. Its sunsets look blue because the dust scatters red light away. It's as if Mars looked at Earth and thought, "No thanks, I'll do the opposite." Now imagine a world with no atmosphere at all, like the moon. There, the sky is pitch black even at noon, not because it's night, but because there's nothing to scatter the sun's light. You'd be standing in bright sunlight, looking up into pure darkness, slightly unnerving, like someone left the universe on standby. Then there are the stars themselves. Not every sun is like ours. Some stars are redder and cooler. Some are hotter and more bluish. If you lived on a planet orbiting a red dwarf, even the middle of the day might feel like an endless sunset. Bit of a win for mood lighting, less ideal for beach holidays. The planet's distance from its star also matters. Too close, and you get a blinding white washout. Too far, and the sky might never be more than a deep indigo. And if your planet has a thick cloud layer, like Venus, the sun might never make a personal appearance at all. Permanent overcast, no silver linings. Chemistry plays a role too. On Titan, Saturn's largest moon, the atmosphere is thick with orange haze. It's mostly nitrogen, like ours, but with methane doing the extra work. The result is a sky the color of diluted squash. And it's cold, very cold. So you'd want your squash metaphor to come with thermal trousers. Some planets may even have skies full of reflective crystals. like frozen ammonia or sulfuric acid. These can create strange visual effects, glows, halos, or even two suns appearing at once. Lovely to look at. Assuming your suit's acid-proof and you're not being pelted by diamond rain. Yes, that's a thing, just not here. This leads us to consider a simple but profound point. There is no one kind of sky. Every planet gets the one it earns, based on its star, its air, its chemistry, and its distance. Ours happens to be blue. For now. For all its beauty and usefulness, the sky isn't some invincible shield. It's a thin, fragile layer of gases clinging to a rock in space. Not exactly the most robust setup. And yet, this slim veil makes Earth habitable, which is impressive, considering it's also completely invisible unless something shines through it. The atmosphere extends upwards for about 100 kilometers before fading into space. But most of what we rely on, the oxygen we breathe, the weather we complain about, happens in just the lowest 10 kilometers. That's not much. If Earth were a football, the breathable bit would be thinner than the paint, and this delicate layer is easily disrupted. Burning fossil fuels adds carbon dioxide, trapping more heat. That warms the lower atmosphere, changing weather patterns and stressing ecosystems. The upper layers, meanwhile, can actually cool in response. So we're managing to make the air warmer and colder at the same time. Quite the achievement. Pollution also messes with the sky's chemistry. Nitrogen oxides from vehicles and industry react with sunlight to form ground-level ozone. Not the helpful kind up high, but the irritating kind that triggers asthma. Particulates from fires and factories reduce air quality and alter how sunlight scatters, which can dull the blue and shift how sunsets look. Then there's the ozone layer itself, the high-altitude shield that blocks most of the sun's harmful ultraviolet rays. It's been recovering slowly since CFCs were banned in the late 1980s, but the process is far from finished. And every now and then, someone proposes geoengineering schemes with all the delicacy of fixing a cracked window with a hammer. It's not all doom, though. Efforts to clean up air pollution have worked in many cities. Skies once yellow-brown now show patches of blue. Satellites track global changes, and there are real-time monitors that can detect spikes in harmful gases. Basically, the sky is now under surveillance, in a good way. Still, the balance remains fragile. It only takes one big volcanic eruption, or a century of industrial growth, to shift things in ways that are difficult to reverse. And the atmosphere, being quite shy, doesn't make much noise about it. It just changes, quietly, persistently, until people notice they're coughing more and seeing fewer stars. This leads us to consider a final perspective. The sky isn't just a view, it's a system. One we live inside. And while it might feel eternal, it's far from guaranteed. Protecting it isn't just about saving the planet, it's about preserving the thin, temperamental veil that lets us live and breathe beneath it. If you want to understand Earth's history, you don't always need to dig down. Sometimes, looking up is enough. The sky has recorded clues about our planet's past. Not with pen and paper, but in particles, gases, and the traces they leave behind. In a way, it remembers things we'd rather forget, and a few we still don't fully understand. One place to find this memory is in ice cores. Scientists drill deep into glaciers and extract long cylinders of ancient ice. Trapped inside are bubbles of air, tiny samples of the atmosphere from tens of thousands of years ago. Like nature's own air quality report, written in frosty handwriting. These bubbles tell us about past levels of carbon dioxide, methane, and other gases. They show how Earth's temperature has risen and fallen, often in sync with changes in the atmosphere. It's a bit like realizing the heating bill and the open window have been linked all along. Who knew? Volcanic eruptions leave sky-based signatures too. Massive blasts throw sulfur dioxide high into the stratosphere, where it forms fine particles that reflect sunlight. The result? Global cooling, strange sunsets, and the odd year without a summer. All conveniently preserved in ice, tree rings, and the diaries of grumpy 19th century farmers. Even the night sky holds ancient messages. Light from distant stars and galaxies carries a record of the universe's past. When that light filters through Earth's atmosphere, it gets slightly distorted and occasionally absorbed by whatever happens to be floating up there at the time. Not helpful for astronomers, but very helpful for atmospheric scientists. The aurora, those flickering curtains near the poles, are another sky-based archive. They're caused by charged particles from the sun hitting Earth's magnetic field. Their patterns and intensity reflect changes in solar activity and, sometimes, the rare tantrums of our nearest star. You can't reason with it, but you can take notes. There are even strange chemical traces in sediments and rocks that hint at earlier skies. Isotopes of oxygen, sulfur, and carbon help reveal what Earth's atmosphere was like long before humans turned up. For example, signs of an oxygen-free sky from billions of years ago. Not a place for a jog, unless you fancy turning blue quite quickly. All of this helps scientists piece together the long story of Earth's climate, weather, and atmospheric chemistry. It's a bit like detective work, except the witness is the sky, and it only talks when frozen or filtered through a spectrometer. This leads us to consider one final thing. The sky changes, but it also stores. Every cloud, molecule, and flicker of light is part of a long, ongoing memory, a record of what's happened, what's happening, and what might come next. For all its complexity, Earth's sky is just one example. If we look beyond our atmosphere, we find other worlds with skies of their own, some thick and toxic, some vanishingly thin, and a few that aren't even blue. It's a reminder that what we consider normal is really just local. Take Mars. Its atmosphere is about 100 times thinner than Earth's, and mostly carbon dioxide. The result? A sky that's often a hazy pink during the day and turns blue at sunset. In other words, the Martian sky has its own version of the color scheme. It just runs it backwards. Because of course it does. Venus, meanwhile, has a sky you'd never want to visit. It's cloaked in thick clouds of sulfuric acid, with an atmosphere so dense it would crush you before the 460 C surface temperature finished the job. Sunlight struggles to get through. If you're ever tempted to book a trip there, don't. Titan, Saturn's largest moon, has a sky rich in nitrogen, like ours, but laced with methane and so cold it rains liquid hydrocarbons. The thick haze turns everything orange. The sun is just a dim smudge, barely visible. A bit like London in February, but colder and with more lakes of liquid methane. Even gas giants like Jupiter and Saturn have skies. Just no solid ground beneath them. Their upper layers are made of hydrogen and helium, with strange weather systems including jet streams, massive storms, and cloud bands that stretch for thousands of kilometers. Imagine checking the forecast, and it just says, windy, forever. On exoplanets, worlds orbiting other stars, The variety gets even stranger. Some have skies filled with silicate clouds, meaning it might literally rain glass. Others may glow red or green, depending on their star's light and atmospheric chemistry. It's fascinating, if a little hard to market as a holiday. Astronomers study these alien skies using spectroscopy, analyzing starlight that passes through a planet's atmosphere. It's a bit like trying to work out someone's perfume by smelling the lift 5 minutes after they've left. Tricky, but surprisingly informative. All these skies, near and far, offer insight into how atmospheres work, how planets evolve, and what conditions might support life. Earth's atmosphere isn't just rare. It might be uniquely stable for complex organisms. Compared to a world where it rains acid or glass, a cloudy day doesn't seem so bad. This leads us to consider our own sky, not as an ordinary backdrop, but as a fortunate exception. A breathable, protective layer that lets us live, breathe, and complain about the weather without immediately bursting into flames. Which, all things considered, is a decent setup. After all the clouds, gases, and ultraviolet trivia, we arrive at something quietly extraordinary. Earth's sky doesn't just look nice, it lets us breathe. The atmosphere might seem like background, but it's more like life support. And unlike most life support systems, it didn't come with a manual or a warranty. The breathable part of the sky, the troposphere, stretches just 8 to 15 kilometers above our heads. That's it. All the oxygen you've ever inhaled, every weather system, every aircraft journey, and airborne insect, they all happen within this thin band. You could drive it in 10 minutes. If it weren't mostly vertical. Oxygen makes up about 21% of the atmosphere. That number matters. Much less, and humans struggle to stay conscious. Much more, and fires become far too enthusiastic. The balance is maintained by photosynthetic organisms, plants, algae, and bacteria, quietly converting sunlight, carbon dioxide, and water into breathable air. They do this without pay, praise, or lunch breaks. The nitrogen, about 78%, does very little in the way of supporting life directly. But it cushions the oxygen, preventing it from being too reactive. It's like the sensible sibling at a party, making sure nothing catches fire. Argon and trace gases make up the rest, mostly standing around, not getting involved. What's remarkable is that this balance is not automatic. It's been shaped by life itself over billions of years. The Great Oxygenation Event, around 2.4 billion years ago, filled the atmosphere with oxygen and killed off most of the life that couldn't handle it. Lovely stuff. Evolution. Always with the plot twists. Today, the air remains breathable, largely because ecosystems keep cycling gases in and out of the atmosphere. Forests, oceans, soils, and tiny plankton work like a global thermostat and air filter. When we disturb these systems, say by burning fossil fuels or removing vast chunks of forest, the atmosphere responds, slowly but firmly. This is why climate change matters. It's not just about hotter summers and rising seas, it's about altering the balance in our narrow, breathable strip of sky. The one thing that all life depends on. Think of it like messing with your own lungs, but expecting someone else to do the coughing. This leads us to consider the fragility of the whole arrangement. For all its size and weather tantrums, Earth's atmosphere is a slim temporary layer. It has a past, a present, and whether or not it has a future depends, at least in part, on us. From space, Earth's atmosphere is barely visible. A pale, glowing sliver hugging the planet's surface. It's often called the thin blue line, not because it's policing anything, but because it separates the livable from the lethal. Above it, vacuum; below it, everything that's ever breathed. The line is thin because gravity holds gases close to Earth. Most of the air is packed into the first 10 to 15 kilometers. Beyond that, molecules spread out fast, and by 100 kilometers up, the edge of space, there's barely anything left. That's less than the distance from London to Oxford. Not exactly far-flung. This fragile layer does more than supply oxygen. It regulates temperature, blocks harmful radiation, and keeps meteors from smashing into our faces. It also scatters light, gives us weather, and holds in the heat needed for liquid water, which, in our line of work, is sort of a big deal. But thinness has a downside. Being small means being sensitive to chemical changes, to heat, to particles we keep pumping out of factories, engines, and chimneys. The atmosphere is sturdy enough to survive a solar flare, yet oddly vulnerable to hairless apes setting things on fire for 150 years. Still, it's resilient. Ozone holes grow and shrink. Carbon dioxide levels rise and very slowly respond to our efforts. The atmosphere doesn't hold grudges. It just responds to physics and chemistry, cause and effect, whether we like the effect or not. Unlike your group chat, it doesn't do mixed signals. This view, the Earth as a blue planet with a fragile veil, is new. Before satellites, we had no idea how thin the atmosphere looked from above. Now we see it daily. Astronauts describe it as beautiful and fragile, usually before returning to a planet still trying to decide whether climate change is real. The thin blue line also marks the boundary between us and space. Cross it, and you enter a place with no air, no pressure, and no helpful weather reports. Yet, despite its indifference, space isn't far. You could drive there in under an hour. You just wouldn't survive the arrival. This leads us to consider our final perspective. Looking up may feel like wonder, but it's also looking out. The sky is not just something we gaze at, it's the edge of everything we know. And beyond it, the universe is waiting. For most of human history, the sky was simply up. It gave us daylight, weather, and the occasional terrifying eclipse. But more than that, it offered perspective. Whether you're a Bronze Age shepherd or a bored teenager lying in the grass, looking up does something peculiar. It reminds you you're on a planet, not just on a patch of ground. When ancient people looked up, they saw patterns, constellations, movements of the sun, the moon, and wandering stars, what we now call planets. They told stories, marked seasons, and slowly worked out that the sky wasn't just decoration. It was a clock, a map, a mystery. Unfortunately, not one with clear instructions. Even now, looking up connects us to something older than civilization. It's the same sky humans have stared at for thousands of years, though now it contains a lot more satellites and the odd billionaire in a jumpsuit. The stars haven't changed, we just got noisier beneath them. Today, astronomy lets us ask bigger questions. What are stars made of? How far away is that galaxy? Could anything live out there? The sky stopped being a ceiling and became a window. Not to heaven, unless you're particularly optimistic, but to the rest of the universe. A place still governed by the same physics, but with much less traffic. This shift in thinking, from sky as canvas to sky as cosmos, happened gradually. Galileo's telescope didn't just magnify objects, it magnified doubt. Suddenly, the heavens weren't perfect or fixed. They had craters, moons, and motion. And Earth? It was just another object in the mix, not exactly ego-boosting. Now, looking up also means looking back in time. Light travels fast, but not instantly. That star you see tonight may have shone thousands of years ago, in some cases millions. It's like receiving very old postcards from a universe that's changed address. Helpful if you're a cosmologist. Less so if you're impatient. Yet, for all our satellites, telescopes, and space probes, most people still look up and feel something quiet. Not fear or awe, necessarily. Just scale. A sense that we're small, brief, and located on a very particular rock, in a very large place. A reminder that most of the universe isn't about us. So when we look up tonight, we're not just seeing weather or stars. We're seeing context. A sky filled with light, physics, history, and unanswered questions. The same sky our ancestors watched. The same sky future generations might one day leave behind. Looking up shows us the sky. Understanding it shows us scale. And scale, well, that's where things get strange. Because our brains evolved to throw stones and find berries, not to compare atoms to galaxies. We're simply not built to picture sizes that span 40 orders of magnitude. Which may explain why nobody's ever described the universe as convenient. Let's start at our scale, human scale. A meter is easy to grasp, so is a second. But go smaller than a millimeter, and things begin to blur. Cells, molecules, atoms, quarks. At the bottom end, we find Planck length. The shortest possible distance that makes any physical sense. About 10 meters. Now head the other way. Buildings, mountains, planets, stars, galaxies. The observable universe is about 93 billion light-years across. A light-year is already a big number. Multiply that by 93 billion. And you've got, well, something impressively pointless to memorize. Put simply, space is large. And it doesn't particularly care if we feel overwhelmed. Yet somehow, the laws of physics remain consistent across this scale. Gravity works the same on apples and black holes. Electromagnetism governs both electric toothbrushes and quasars, which is handy because it means we can use equations to describe both the behavior of electrons and the structure of the cosmos. Maths, it turns out, has no sense of proportion. This also means that tiny particles influence giant systems. The arrangement of quarks and electrons determines the chemistry of life, and the mass of invisible particles, like neutrinos or dark matter, shapes entire galaxies. It's a reminder that the very small and the very large are not separate worlds. They're joined, intimately. And whether you like it or not, scale also warps time. Fast for atoms, slow for continents. Light takes nanoseconds to cross a room, but millions of years to travel from distant stars. Mountains rise and fall, while stars orbit their galaxy. Our human lives, meanwhile, are a flicker. Long enough to watch a Netflix series, short enough to be invisible from space. So when we talk about the universe, we're referring to a system that contains all of these scales at once, from the subatomic to the supergalactic, from femtoseconds to billions of years. A place where time and size don't stay fixed, and where perspective is everything. Which is great if you enjoy existential vertigo. This leads us to consider one final thread. Amidst all this scale and strangeness, how do we make sense of our place? How do we find meaning in a universe that clearly wasn't designed with us in mind? To answer that, we'll need one last idea: and it's surprisingly close to home. And that brings our journey to a gentle close. If you're still with us, you're welcome to drift off with another of our sleepy deep dives. Until then, rest well and good night.